Hey guys. So today we're going to do permutations and combinations. I'm very excited to go over this with you. I've been hyping it up all year, so I hope you come along with me for this ride. I think this content is rather difficult, which is why it's extra credit this week. So I'm going to post this lecture along. I have 4 lectures I'm going to post this week, along with the 4 guided note sets. And actually, as of doing this lecture, I'm not actually sure if I'm going to give you extra credit for doing the assignments. I'm kind of inclined toward no. And then there'll be a test that will be an extra credit test. And it won't be a huge number of points, but I might give you something like, I don't know. It'll be some extra credit. So if you go through this with me, you'll get something worthwhile. And then, next week I might also do some more extra credit for statistics, because this is a probability week, right? There's statistics and probability. Probability is calculating what we think will happen before things happen, and statistics is trying to figure out what's going on after things happened. So I thought it might be cool to do 1 week of statistics here to give you guys a little bit of background, so you can think, this is what this whole statistics thing is about. And then next week we can do this. What probability is about. The next week we can do the same thing with statistics. So I just found something in my glass of water that I'm not happy about. All right, moving on. So this is 11.1 Permutations and Combinations, and we first want to talk about the fundamental counting principle. And the idea of the fundamental counting principle is just this. If we have multiple things that can be done in various ways, then we can find the total number of ways by multiplying all those combinations together. Okay? So if decision M, and M here is just a random variable, it doesn't have any special meaning, there's decision M. We could call it decision X or decision Y. Don't get hung up on the M. But if decision M could be made M ways, and decision N can be made N ways, then the 2 decisions can be made M times N ways. Okay? So I'm going to give you a little example of that. These examples are great, but they all use big numbers and assume that you understand things on a more fundamental level. And I don't want to start with that. So let's say that we have two kinds of pets. We have dogs, and we have cats. Actually, I'm just going to do C for cats to save writing time. Dogs and cats. And let's say that there are 3 ages, and they are young, middle, and old. Okay? So if I wanted to ask you, how many different combinations of animals can there be between pets and ages? The answer is 6, and I want to show you why that is. Well, first, this is called a sample space I'm writing out. I could have dogs, and those dogs could be young, they could be middle-aged, or they could be old. I could also have a cat, and that cat could be young, middle, or old. So that means my combinations are dy, dm, do, cy, cm, co for 6 combinations total. So that's the same thing as doing 2 times this 1, 2, 3. So 2 times 3 gives me the total number of combinations, or ways, we often say. If I added another category to this, let's say another thing we could talk about with pets is bred. Let's see, source. And are they from a breeder, B, or are they from a let's just say a store, or like something sad like a puppy mill? So the other come from B, a breeder, or S, a store. Well, how would I add that on here? Well, for each of these combinations, dogs that are young, dogs that are middle-aged, dogs that are old, I have to also consider that they could also be B or S. So I added another branch for each one. B, S, B, S, B, S. As I'm writing this, I'm realizing that I chose BS. That's great. So BS, BS, BS. I think that's the most time I've ever said BS in a lecture. Could have even made it SB, Don. Anyway, and if I count this down, how many do I have now? Like I have DYB, DYS, DMB, DMS, DOB, DOS, etc. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 combinations now. Well, that's the same thing as I have 2 pet combinations, or species, 3 age combinations, and I have 2 source combinations. So if I do 2 times 3 times 2, 2 times 3 is 6, 6 times 2 is 12. So multiplying these gives me 12, which is the total number of combinations that I can get from these. Okay? So if I ask a question like, the ice cream shop offers a choice of 3 cone sizes, 15 flavors, and 8 toppings. How many cones are possible if you can only choose 1 flavor and 1 topping? Okay, so what can I choose? I can choose between 3 cones, 15 flavors, and 8 toppings. It would be ridiculous to write this out in a sample space like this. But now we know the fundamental counting principle, I could just do 3 times 15 times 8, and if I 3 times 15 times 8, I get 360. Okay, so that's kind of interesting to know, right? And when you this is 360, and this is used in advertisements, right? You will go to a restaurant and it'll say something like over 400 combinations of blah blah blah, or go to some kind of I don't know, like a clothing place or something like that. So being able to calculate the total number of ways does get used in common situations, I would say. Okay, a Virginia license plate consists of 3 letters followed by 4 digits. How many different license plates are possible? Well, 3 letters. Okay, well, how many letters are there? There's 26. So that means we're doing 26 times 26 times 26, or 26 to the 3rd power. And there are 4 digits. And this one can be a little tricky if you're not thinking about it right. Like how many, if I have 4 digits, X, 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 how many different combinations of digits are there? Well, that's just the same as counting all the combinations, okay? And that's 10,000. Now, you might say, why is it 9,999? Right, that's as high as we can go. Why is it 10,000? Well, we have to include the option where these are all 0, right? It's possible that if you have a license plate, it could be 0000, right? So it's 26 to the 3rd power times 10,000, and I actually did this one ahead of time to make sure that I was doing things right on this. 26 to the 3rd power times 10,000, and that is, let's see, if I put a comma, let's see, 175,760, 175,760, 000. So 175,760,000. And the thing with permutations, combinations, and sample spaces, fundamental counting principle, ways, and all that, is you do end up with huge, huge numbers. In fact, in one of my statistics classes, our numbers were so big that they would crash our computers. And so we had to figure out ways to break up the math into smaller bits so that the computer could handle it and tell us how many different combinations there were. So sometimes it's not uncommon to get huge numbers when you're doing things right, okay? It seems scary, right? Because there's no way to check your math, right? You can't. There's no way to check this number because you're not going to do this manually, probably, right? So that could be scary. Nick Scientist has a section with 12 true or false questions. How many different ways can Nick answer these questions? Well, how many ways can you answer a question? 2, right? It can be true or false. Let's say this is question 1. Well, in question 2 can be true or false. True or false. So you can see this can actually be written as a sample space, just like the pets example. And each layer has 2 options. So that means we're multiplying 2 12 times, so it's just 2 to the 12th power. Oops, didn't do that. Okay, 2 to the 12th. So 4,096. So that's 4,096. So this is really interesting to me because you've a science test. It's just 12 true or false questions. And so you might think, how many combinations are there? But it turns out that if you all took a science test and you randomly selected true and false, the probability of 2 of you having identical answers is very slim, right? If you have 24 students in a classroom, let's say, and 4,096 combinations, it's not very likely that 2 students will end up with the same answers, which is why, colleges, well, teachers in general, are very suspicious if several students have identical tests, whether it's legitimate or not, because it's just not very likely. Unless the questions are all easy, of course. Then it becomes very likely. But if you have 2 people who did poorly, and they, let's say they scored like a 30%, and those 2 people with a 30% have identical answers, well, that's extremely suspicious, right? You both have no idea what you're doing, and you, okay. And you got the same stuff. All right, so let's move on to talk about factorials. So factorials are written as n, and this can be any number, right? It's just like x. You tend to use n for counting, with an exclamation mark. And so here's some factorials I'm just going to type out right here as an example. Here's 3 factorial is equal to 6. 5 factorial is 120. 10 factorial is 3,628,800. And if I do like 100 factorial, oh, look at how ridiculous that is. Can this even do 1,000 factorial? Yeah, so you look at, okay, so this is a great example. I did a good job. Factorials grow very, 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 very quickly. And you can, like, this is 10 times 10 to the 157th power. If you've taken chemistry, that's a 1 or a 10, no, a 1 with 157 zeros after it, right? And this is undefined, not because we can't know what it is, but because 1,000 factorial is too big for Desmos to handle. It can't handle that math, okay? So, actually kind of curious, can you do 500 factorial? Oops, not 5,000. 500? No, not even 500 factorial. Okay. So, that's interesting to know. So what is a factorial? The math behind a factorial is actually very easy. It's just the product of all natural numbers from 1 to n. Okay? So if I say 9 factorial that means I'm doing 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, obviously not times 0 because then everything would be 0. And if I do that math, I'll just do one of these. I guess I'll switch this one to 9 factorial. 362,800. It's actually kind of interesting how, because it's times 10, so you'd expect to be off by a factor of 10. Not as coincidental as I initially thought. 362,880. 362,880. Okay? So that's that. I'm not going to go through and do all these factorials. I'll talk about 17 factorial over 11 factorial conceptually, because it's just typing things in a calculator. There's no reason to go through and do these. Waste of time. Well, what's 17 factorial? That's 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10. This is gonna times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 17 factorial divided by 11 factorial. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, I know I can just type this in a calculator, but I want to demonstrate something to you conceptually, okay? This looks like a lot of math, but there's a lot of canceling we can do, right? There's a 1, a 1, cancel. Actually, let me switch it to red. Cancel the 1s, cancel the 2s, cancel the 3s, 4s, 5s, 6. Like, you cancel everything, right? 11 and lower. So actually, you don't do any division. What you actually do is use 17 times 16 times 15 times 14 times 13 times 12. That's what this math is the same thing as this math right here, okay? That'll be important in a minute. 0 factorial, special rule, 0 factorial is 1, okay? Otherwise, we'll end up with a lot of funny answers when we do permutations, okay? And permutations are written as NPR, okay? And a permutation is an arrangement or line of objects in which order matters. And so when I say N pick R, that's the P. People disagree on how you say the P. Like, no one can seem to agree on it. But you could say N permute R or N pick R or whatever you want. And the math for it is N factorial over N minus R in parentheses factorial. So what is... And the thing is this. I'm going through the formula real quick because I don't use the formula, okay? I try and work intuitively because you are not going to remember NPR equals N factorial over N minus R factorial. You're never going to remember this. And if you think you will remember it, ask yourself if you remember the formulas for geometric and arithmetic series that we went over earlier this year. If you do, you're very impressive. But my guess is that almost all of you do not. And that's okay, right? That's why I try to talk about the intuition behind things, because maybe you can derive the intuition. Maybe you can't, but, I can only do so much for you. Let's go, okay, I'll write again here for reference. It's N factorial over N minus R factorial. And then the N is the total number of objects available. So how many things are we sorting in an order? And R is the number of objects to use for the arrangement. So if we're using all of our objects for the arrangement, then it's N factorial over N minus R, but N and R are the same. So it just becomes n factorial, right? Because if n and r are the same thing, anything minus itself is 0, and we just went over the special rule, 0 factorial is equal to 1. So npn, where r is equal to n, is just n factorial. That's how many ways we can organize things. So there's a good chance right now you're extremely confused, and it's totally okay, because I went over the math first, and now I'm going to go over the intuition of things. And I want to try and... before I go in... this number 5 is like, this is kind of a big word to permute, so I don't want to do it just yet. I'm going to give you a simple example. So let's talk about a word like... let's talk about hair. Okay. For some reason, I was going through different kinds of body parts, and this seems like the best one. So, hair is an appendage? Is hair a body part? I don't know. We're going to call it a body part today. So, what I'm asking you is, how many different ways can I order this? There's H-A-I-R, right? But I could also flip the I and the R and make it H-A-R-I. Actually, you know what? Let's do... I'm gonna do something smaller. Let's just do the word fin. Okay, that's another body part we all have, right? We all have fins. And I want to ask you, how many ways can I organize the word fin? Well, I can have F then I then N. I can also do F then N then I, right? I can switch these. So F N I. And I could also I could put the I first. If I put the I first, I could do F then N. If I've already chosen the I first, I can flip the F and N and do N then F. And if I choose the N first, I can do F then I. But I can also do N, then I, then F. So I think those are all the combinations, right? There are only 3 options to choose first: F, I, and N. And after I've chosen the first letter, there are only 2 potential organizations, right? I can have the 2 remaining letters in one order, or I can flip them. And if I do all those combinations, there are 6 combinations. Well, 6 combinations is the same thing as 3 factorial. So notice I had 3 letters, and 3 letters in the word ends up being 3 factorial. I went down to fin because with hair, how many combinations are there? How many different permutations are there for hair? There's 4 factorial. And 4 times 3 times 2 is 24. And as I started to do the work, I recalled this fact and realized I would much rather write out, 3 factorial is 6, and I'd much rather write out 6 combinations to do my example than 24 combinations to write out my example. So it just doesn't seem like a very good use of time, okay? So what's the logic behind this? Like, how can we take... yes, I took the time to write out all the combinations here. But how could I know that this math isn't just coincidental? Okay, here's the logic behind it. With each step, let's think of a word like fin, and think of it as like a hangman game. All right? And what I'm going to ask you is, remember, let's go back to our fundamental counting principle. How many ways can we do something? And then once we know how many ways something can be done, we can multiply those ways together to get our total number of ways. So if I have fin, F-I-N, for my first letter, how many ways can I pick a letter for that? Well, there are only 3 options, right? F, I, and N. So there are 3 ways that I can pick that letter. Then, whatever I picked, it doesn't matter, okay? Whatever I picked, whether it's F, I, or N, let's figure out these first letters. How many different options do I have now? Well, if I picked F, I only have I and N, 2 options. If I have picked I only have F and N, 2 options. If I picked N, I have F and I, 2 options. So no matter what, after I pick my first letter, there are only 2 letters left that could go in the second spot. And then what's left for the third spot? Well, if I get rid of my second letter here, there's only 1 letter left, right, for each of these that can be picked. So there are 3 ways to pick the first letter, 2 ways to pick the second letter, and only 1 way to pick the third letter. That's why it's 3 times 2 times 1, or 6, which is the same thing as 3 factorial. Okay? So for dinosaur, the logic is, this is a 1, 2, 3, 4, 5, 6, 7, 8 letter word, okay? 1, 2, 5, 6, 7, 8. How many ways can I pick my first letter? Well, there's 1, 2, 3, 4, 5, 6, 7, 8 different letters I can pick. So there are 8 ways that I can pick my first letter. Now I've picked a letter, so my second letter is 7 ways. And I've picked 2 letters, so it goes down to 6, 5, 4, 3, 2, 1. So this is just 8 factorial. Okay? That's the most basic situation, and that's why we use factorials, to keep track of how many ways something can happen. Now, right away, things are going to get more difficult with number 6. 7 students are competing in a geography bee. How many ways can they finish in first, second, and third place? So wait, I have 7 people. Here's my people. 3, 4, 5, 6, 7. But the question just says, how many ways can they finish in first, second, and third place? So I only have 1, 2, 3 slots. How do I work that out? Well, the logic is the same. How many, I have 1, 2, 3, 4, 5, 6, 7 students. How many students can get, if I go in order, how many students can get first place? 7 of them can get first place, right? But once I've picked one of them for first place, how many are left for second place? There are only 6. And then once I've picked someone for second place, right, I've picked the first person for first place, I picked my second place, how many people are left for third place? 5. And now I'm done. So it's just 7 times 6 times 5, which is 210. That's how many different ways that they can finish in first, second, and third place. This math right here, that's a 0 for 210, that's actually the same thing as this formula, this permutation formula. Let's try it out. N is the number of objects available. Okay, so I have 7 objects available divided by N minus R. Well, I already said N is 7 because there are 7 objects available, minus there are, how many objects are being used for arrangement? Well, 1, 2, 3 objects are being arranged. So this is 7 minus 3. Factorial. Well, if I work this out, 7 factorial, 7 minus 3 is 4. So it's 7 factorial over 4 factorial. If you think about our example before where I did the 17 factorial over 11 factorial, and I canceled out all the numbers 11 and lower, this 4 factorial right here is going to cancel out all numbers 4 and less from multiplication. Well, if 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, and I get rid of all the numbers 4 and less, what's left? 7, 6, and 5. And I'll prove it to you. 7 factorial divided by 4 factorial is 210, which is the same thing as 7 factorial over 7 minus 3 factorial. So notice these are the same things, and that's the same thing as 7 times 6 times 5. All these end up being the same thing. Okay? So the intuitive understanding, I find this, just doing 7 times 6 times 5 and understanding where these numbers come from thinking about this intuitively and how many ways I can pick things, I personally find that a lot better than using the formula. Now, sometimes things get really scary, and you want to use the formula to make things simpler, and it's okay. But the more fundamental understanding, I was trying to avoid the word fundamental, but I used it anyway, can save you, can help ingrain exactly what's going on here, okay? Because I did permutations and combinations when I was in high school, and I can tell you that I had no idea what was going on, okay? And in fact, I did permutations and combinations in my school program, and I got the questions right because I studied a lot, but I still didn't really understand it. It actually wasn't until I found this YouTube series called Don't Memorize that the intuition behind it was explained to me, and I thought, well, why didn't someone just say that sooner, you know? The explanation I gave you is, I think, well, it's a lot better than anything anyone showed me before I found that video. And it's like a 26-part video series, and it treats you like you're a total moron. From the first video, it's like, hey, you're an idiot who doesn't get this. And sometimes that's what we need, right? Sometimes I just need to be treated like I'm an idiot who doesn't understand anything. Because sometimes that's what I am. Okay. Easy one. Melanie is taking 4 classes this semester. American History, Algebra II. Hey, good for her. AP English, and Chemistry. How many ways can these 4 classes be arranged on her schedule? It's just 4 factorial, right? We have 4 slots and 4 items. Simple math. There are 16 players on a baseball team. How many ways can the coach make a 9-player batting order? So we got 16 players, but only 9 spots. So it's just going to be 16 factorial over, how many spots do we have? 9. So 16 minus 9 factorial. Okay, and that's the same thing as having 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what's going to be here? 16, 15, 14, 13, 12, 11, 10, 9. I almost went back up to 11. 8. Okay? And if I do 16 minus 9, what do I get? This is now 16 factorial over 6 minus 9 is 7. 7 factorial. Well, that's the same thing as if I divide by 7 factorial, I get rid of everything 7 and less, right? So if I have 8 here, 7 and less got cut out, that's my end. So this is multiplying this together is the same thing as doing this math right here. Okay? So I don't know if I need to do this. 10 though. So this is, if you're feeling confident, great. If you're not, I would go back and repeat the last 10-15 minutes of what I've said and go through the examples on paper along with me, because this is going to get harder. So what about permutations with repetition? We have an issue here. In every problem leading up to now, we've had unique cases, right? This is 16 players. 16 unique players, right? There aren't 2 Freds or 2 Melanies on a team. Careful to pick, I know, students of mine, so none of you think that you're my favorite baseball player. What if I have 2 people who are the same? We're talking about how you can order things. If I have the word I don't know. Let's just say I have which is how some of us might be feeling right now in life, and I want to know how many ways can I order How many ways can I order this? There's only one way. Right? There's only one way, because no matter how I move these around, it's exactly the same, right? And similarly, if I decide to lighten up on the a bit and make it how many ways can I order this? It's easier than you think. The A's are all the same, right? The H is the only thing that matters. In what position can H be in? It can be in here, 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 here. Can I have even 5 positions? That's all that matters. H can be in 5 positions, otherwise the A's are interchangeable. So when I say how many different 10-letter arrangements are possible using the letters in the word automobile, we have to take into account something. So it's 10 letters. And the way I like to do this is to say, we have 10 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I pick those 10 spots, that's 10 factorial, right? Divided by, and now the intuition here is to say how many of these letters are up for ordering, right? Because our formula, which, it's not written there anymore, so that's stupid. Wait, I'm screwing this up. Okay. That's still not quite right. Wait, I'm going the wrong way. Yeah, it's okay. That's pretty acceptable. How many are up for ordering? Well, before we talk about that, let's talk about an intuitive way to handle this, okay? If I order all 10 of these, aren't there some combinations that don't matter? Okay? It doesn't matter if these O's flip. So what we say is, how many duplicates are there? Okay? Well, with every combination, I don't want to write automobile over and over and over again, okay? With every combination where I write automobile, but I flip the letters around, there'd be 2 O's that could be flipped, and it doesn't make a difference. So that means there are twice as many combinations by doing 10 factorial than we need. Or than are really possible, right? Because the double O's. So you divide it by 2. Or actually, it's 2 factorial. But that 2 factorial is just 2. So same thing. And that's how we account for the fact that the O's are doubled up. That's the same thing as 10 factorial divided by our n minus r formula. 10 minus, well, how many letters are available for ordering? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, right? These aren't available for ordering because they're doubles. So it's 10 minus 8 factorial, which gives us the 10 factorial over 2 factorial. I find this a little hard to wrestle with and grapple with intuitively. This makes sense to me intuitively, so I prefer to think about things that way. What do I have disappear? Well, I have 2 doubles here, PP and AA. AA. And I have PP and AA. Well, first, it's 9 letters, so I have 9 factorial. And now there are 2 pairs that can be doubled up. So that's the same thing as dividing by 2 factorial twice. Okay, for my double P's and my double A's. So I hope I've made that somewhat intuitive for you. The last thing to talk about is combinations. And in combinations, oh, there's something I didn't erase. Order doesn't matter. Okay? And we have NCR. And we read NCR as N choose R. And what we're trying to say is, what if I have, this first example is good. Natalie has 16 close friends. How many ways can she choose 5 to be brides in her wedding? That might sound a lot like the previous question with permutations, right? I said there are 16 players on a baseball team. How many ways can the coach make a 9-player batting order? Natalie has 16 close friends. How many ways can she choose 5 to be bridesmaids in her wedding? Don't those sound like the same kind of question? There's a big difference, though. In the baseball team, it says batting order. So that means it matters if I put Melanie before Fred or Fred before Melanie, because I want to know who's first batter. This question down here, we're almost back in the game. There we go. This question right here, it doesn't matter. The bridesmaids don't have like a rank or an order. They're all equivalent. They're interchangeable. So order doesn't matter. It doesn't matter whether I pick Natalie's best friend Janie before, her second best friend Erica before, they get into a fight and then aren't friends anymore in 2 weeks anyway. So our formula is a little different. It's n factorial divided by, we still do the n minus r factorial, but we also divide by r factorial, because we don't care about how things are ordered. So let's do this problem, and I'll try and make it as intuitive as possible. She has 16 close friends. How many ways can she choose 5 to be a bridesmaid in her wedding? So the idea is we have 5 spots. Okay? For spot 1, she can pick 16. Spot 2, 15, 14, 13, 12. So the logic is the same. So what is this the same as? This is the same thing as 16 factorial divided by 16 minus 5. Factorial, because everything 11 and lower is missing, right? That's a 16 minus this 5. But we also don't care how these are arranged. I don't care if it's 16, 15, 14, 13, 12, or if it's 15, 16, 14, 13, 12, or if it's 14, 13, 15, 16, this is 13, 12, right? It doesn't matter what order these are all picked. So I have to get rid of the concept of ordering. To get rid of the concept of ordering, I have to think about how many ways these can be organized, because I don't care about the differences in the orders. Well, how many ways can I organize 5 things? Isn't that just 5 factorial? Which is our r right here, r factorial. So this is also divided by 5 factorial. 16 factorial divided by 16 minus 5 factorial divided by 5 factorial. And if I do the math for that, 16 and 5. 16 factorial divided by 16 minus 5 factorial times 5 factorial. It's 4,368. Notice if I care of the order, if I said that She has 16 friends, and she's going to pick 5. Maybe they're all going to go down the aisle together at the wedding. And she wants to figure out what order the bridesmaids are going to walk down the aisle in. Then this is the math we'd use. 524,160 combinations of ordering. But if we don't care the order, if we're just picking bridesmaids, and we don't care about them going down the aisle, then this is the math. There are 4,068 combinations of friends. And this is why it's very important to follow Mr. Dufresne's life advice and not have a lot of friends. Especially during the pandemic, there's no one for me to miss, except for you guys. Except for you guys, of course. I miss you guys. It's not you. There's something else. Oh, in R, this is a program that I use for my program in statistics, there's actually a command I can just use. Choose 16,5 like that. Look, 4,368. So I actually don't do the math. I don't even type it in a calculator. I just type this command right here and it does the combinations for me. If you want this program, it's just called R. But I was really surprised. Up here you can see me fiddling with things. I was trying to figure out what's the permutation command in R. And I guess there isn't an inbuilt one, or at least I can't find one. I did a Google search and I couldn't find anything. There are packages. You can add stuff. But there's nothing inbuilt. And that's weird to me, because it is a statistical program. I'm also still drinking that water that has something floating in it, because, I don't want to get up and get water while I'm doing this lecture recording. Gross. Okay, so let's do one more example, I guess. There are 24 students in Kyle's kindergarten class. How many ways can you choose 8 to attend his birthday party? So I only have 8 slots. And so for the first slot, I could choose 24 people, then 23 people, then 22 people, 21, 20, 19, 18, 17. Okay, so we have 24 factorial divided by 24 minus 8, right? 24 minus 8 factorial, that's the same thing as 16 factorial. Notice how we're missing everything 16 and lower. That's why this makes sense intuitively. These two things are connected. And then, how many objects do we have? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 objects that we're picking, so we have to also divide out the 8 factorial to make sure that we're not counting ordering, right? If Kyle's friends are going to his birthday party, it doesn't matter which order he invites them. It doesn't matter which order they attend, unless they don't want to miss cake. I've actually never been the kid that misses the cake, but it's a fear of mine. Not even because I missed the cake, Like, I like cake. But the real fear is just standing there without the cake and feeling left out. No one wants to feel like that. Fun fact, I finished my classes 2 weeks ago. And I got A's in both of them, just barely, with some generous curving from one of the professors at least. And so as a result of finishing classes, I have more time to do some other things. And I bought some Dungeons & Dragons books. I've been reading through the rules of modern Dungeons & Dragons, and I'm actually making my wife and my son, Roman, make Dungeons & Dragons characters so we can do a Dungeons & Dragons family campaign. I think it's going to be a lot of fun. But Roman declared... I told Roman to come up with a backstory for his character, and I was really impressed because he said that, he wanted to play a halfling, and he said his character... the character's family was murdered by a red dragon, and the character joined the military to become strong and become a dragon hunter. And after slaying many dragons, now his character resides in a castle with the favored military members, and they just sit around and eat cake all day. So that's the mind of my 4-year-old. Slaying dragons, living in a castle, and eating cake. Okay. So I won't go... It's the same thing over and over again, so I won't keep going. I hope that's clear for you guys, and I'll see you in the next lecture. Oops.